Hello, today we're going to talk about heat and temperature. Okay, so this section introduces us to thermochemistry, which is anytime we are dealing with heat entering or exiting a system, and it could be a chemical reaction or a physical process, as long as there's matter involved, then it falls under the umbrella of thermochemistry. Now I do want to briefly review the difference with kinetic energy and temperature, which we've talked about before. But kinetic energy is the energy of motion, and temperature measures the average kinetic energy. So if you think about if we have a low temperature, the particles are moving slowly, and it's hard to draw on a flat screen that the particles are moving very slowly. But if you have a higher temperature, the particles are moving really fast. I'm going to try to do bigger lines. So this would be a high temperature. So the particles are moving very quickly. Okay. And it's an average. So not all of those speeds are going to be exactly the same. Like each particle is not going the exact same speed. But on average, these ones are moving much slower, and the high temperature ones are moving faster. And so that's temperature. Temperature is measuring how quickly the particles are moving on average. With temperature being average kinetic energy, we know that some particles are going to have a lower speed and some particles are going to have a higher speed. So we can graph that in something called a Maxwell-Boltzmann distribution, which tells us on a graph here, the number of particles are on the y-axis, and the speed of the particles is on the x-axis. And so at a particular temperature, you're going to see almost like a bell curve. It's not exactly a bell curve, but it's kind of spread out like that, where your average is going to be usually somewhere in the middle. Okay. And then if you were to do some more complicated math, you could find the area under the curve to tell us the total number of particles. Okay. So again, the average is going to be in the middle, but you still will have some particles that are moving very slow and some particles that are moving very fast. So some particles have a low kinetic energy and some have a very high kinetic energy. But we're looking at the average. Now, let's say that I'm going to do this again. I'll do it like this. Okay. Actually, let me make it a little lower just to make my life a little easier. There, perfect. So now let's say that is our normal temperature. At a lower temperature, you would kind of squish the whole graph this way. So it's going to look like this. That would be a lower temperature. And if you were to, again, do some complicated math and find the area under the curve, you would have the same exact area under that curve as you would for the original temperature. But it's just all shifted to lower speeds. Okay, so your average is lower temperature, but the same number of particles total. Now, if you were to do a higher temperature, the graph gets more spread out. Okay. Your average is higher, but if you were to do the area under the curve, you would still have the same number of particles. And so these are called Maxwell-Boltzmann distribution curves. As long as you have the same sample of your matter, okay. If you shift the temperature lower, the graph squishes left, and if you shift the temperature higher, your graph spreads out to the right. And the amount of space underneath the line is the same, no matter what temperature you're at. Now let's talk about heat. Heat is energy, okay? And so we were talking about temperature as specifically kinetic energy. Heat is another specific kind of energy, where it's energy that is transferred between two objects due to a temperature difference. So you might have an object that is at a high temperature, and then you place something that has a low temperature inside of it. Like if you take a warm cup of water and you put an ice cube into it. Whatever thing is at the higher temperature is going to transfer some of its kinetic energy to the substance at the lower temperature. And so the amount of energy that is transferred between the two is heat. So that much is the heat. And eventually it'll reach what's called thermal equilibrium, where it will continue to transfer heat until they both reach the same temperature or the same average kinetic energy. So heat is always an energy that is transferred between two objects because of their temperature difference. Now, we've talked about these before. Let's quick review. Endothermic is when heat enters the system. And exothermic is when heat exits the system. And we can show that on a reaction if we have reactants and products. If you have an endothermic process, heat is on the reactant side. So this is endothermic because the heat is entering. Or if heat is being released, exiting the system, then the heat will be shown on the product side, and that would be exothermic. Now, it doesn't have to be a chemical reaction. It could be a physical process. You could have something like liquid water changing into gaseous water. That is a physical change because it's still water. You're just changing state. But you have to put in heat into the liquid water to get it changed into a gas. So that is an example of an endothermic process. Now, there are two main units that we use for heat, joules and calories. These are units for heat. They're also just units of energy because heat is just energy, a specific type of energy. Joules are the SI unit for energy, and we're going to see that most often in this class of joules. And you might also see kilojoules. So 1,000 joules is equal to 1 kilojoule. But calories are what we see a little bit more frequently in commercial applications, and food labels have calories on them. And so 1 joule is equal to, 1 calorie is equal to 4.184 joules. And calories are just based off of water, using water as our baseline measurement. So we're measuring how much water changes temperature with a given amount of energy. But joules is a standardized SI unit, and we're going to use that a little bit more frequently. But this is how you might convert between calories and joules. Now, I will say, if you look at a food label, those are actually kilocalories. Now, I know on your food label it says like maybe your candy bar is 250 calories. And this is in the US. That actually means it's 250 kilocalories. Some countries will actually label it kcal for kilocalories. But some countries will even use joules or kilojoules on their food labels instead. So when you see big C calorie on a food label, it really does mean kilocalories. Now let's talk about specific heat. Specific heat is the amount of heat it takes to raise the temperature of 1 gram of the substance by 1 degree Celsius. And so this helps us to standardize and compare how much different objects change their temperature. So if I have 1 gram of a substance, then I'm standardizing it. So if I have 1 gram of water, it's going to be very different than 1 gram of aluminum, okay? And so how much heat you need to add to increase, 1 gram samples, to increase it by 1 degree Celsius. These two objects, because they are different types of matter, they require different heat, different amount of heat to change their temperature by 1 degree. And water is a good insulator, so it takes a lot of heat to raise its temperature. So it can take lots of heat without changing temperature. Aluminum and most other metals are good conductors of heat. And when it has a good conductor of heat, it doesn't take much heat to change the temperature. It increases temperature really quickly, but it also passes on the heat very quickly. So passes along heat well. And an insulator absorbs heat very well, holds on to heat well. And so insulators tend to have very high specific heats. We're going to use the letter C, lowercase c, for specific heat. So insulators have really high specific heat. Conductors have very low specific heats because it does not take very much heat to change their temperature. Okay, so we're going to get down to this equation then that helps us relate heat to temperature and mass. So we've got this Q equals mc delta T, where Q is the heat, and we're typically going to be using joules. M is the mass in grams typically. C, we said, was the specific heat. And delta T is the change in temperature. Whenever you see this triangle, it's a Greek letter delta, it means there's a change. Okay, and so they're related through this equation, Q equals mc delta T. And this tells us that the heat involved in a particular process depends not only on the size of the object, the type of matter, and how much it's changing temperature. Okay, so let's do a quick example of this. Let's say I have a substance that is 100 grams, and let's just say it's water, because I know water's specific heat is 4.184. And I want to know how much heat it's going to take to change the temperature of that 100 grams of water by 5 degrees Celsius. I can use Q equals mc delta T. So I plug in my 100 grams, plug in my specific heat, and plug in the change in temperature that I'm looking for. And you just need to multiply. And so when you multiply, you get 2,092 joules. Now, if I were to put that in kilocalories, for example, this is equivalent to 0.5 kilocalories. So like if you're reading a food label, it would say like half of a calorie on the food label. So just to put it in a little bit of perspective. So that would be how many joules would be involved in that process. So to wrap up this section, how we measure heat is what we call calorimetry. So measuring heat. And the device that we use to measure heat is called a calorimeter. Okay. And so typically you're going to see some kind of insulated container. And the calorimeter, your reaction, so let me show like the insulation there. Your reaction or your process will be occurring inside the calorimeter, and then you're going to have a thermometer because you need to be able to measure the change in temperature. Now, I will say that your thermometer is always part of the surroundings. Remember we talked about system and surroundings? Your thermometer is always part of the surroundings. You won't ever be reacting the thermometer. So the thermometer is measuring the surroundings. If your process is releasing heat, then the thermometer will be gaining some of that heat, and so it will show an increase in temperature. So exothermic processes show an increase in temperature because the thermometer is part of the surroundings. Now, if you show a decrease in temperature, it must be an endothermic process because the heat is going out of the thermometer and out of the surroundings into the substance. It'll be endothermic. So make sure that you know that your surroundings is your thermometer and the air and the container, and the system is what's actually going on in your reaction or your process that you're measuring. And so, and typically you want to have a lid, or try to have a lid to keep it as insulated as possible, because a big source of error when using a calorimeter is the loss of heat to the surroundings. And we don't want to lose any of that. We want to measure all of the temperature change that we can to be able to measure the heat accurately.